what is the fluoride ion concentration and approximate pH of a solution that has 0.15 molar HF and 0.05 molars of HCl? Let's see if we can figure that out. Now, HF is, of course, a weak acid, which means that it is going to exist in an equilibrium way between its two dissociated ions, H plus and F minus. HCl, in contrast, is a strong acid, which means it's going to have a one-way arrow and dissociate completely to form H plus and Cl minus. Now, if we want to calculate the pH of just a solution of HF, the way we would do that is by using its Ka and an ice table, kind of like we've done with examples like that in the past. But this is different, because this is not just a solution of HF. This is a solution of HF in which we've also added HCl. And HCl dissociates to form H plus and Cl minus. As we look at H plus and Cl minus, you might realize that H plus here is a common ion with the H plus up here. In other words, the H plus given off by HCl down here is going to come in here and feed back, pushing this a little bit to the left, more than it would normally be. And that will affect the pH. Hopefully you're okay with that. So this is the common ion effect, when I have two things in solution, and the second thing dissociates to give an ion that is in common with one of the ions on the right for my other thing in solution. You good with that? Alright, let's see what we've got here then. So it tells me, by the way, that the Ka of HF is 6.8 times 10 to the negative 4. In order to do this, I'm going to have to do an ice table. So I'll go ahead and write this out. The difference, however, is that the initial concentration of H plus is not 0. Now in past ice tables, it has been 0, and indeed it would be 0 if all we had in the solution was HF. But because we have this HCl, and HCl is a strong acid, it will dissociate completely, and at initiation, all of this H plus will feed back into here. So at initiation, the concentration of H plus is going to be not 0, right? So what is it going to be? Well, HCl starts out as being 0.05 molar, and because once again it's a strong acid and it's present in a 1-to-1-to-1 ratio with these ions, it's going to dissociate to give an equivalency of 0.05 molar H plus and 0.05 molar Cl minus. We don't really care about the Cl minus. This guy is the one that is a common ion that feeds back. So at initiation, the concentration of H plus is going to be 0.05 molar. Make sense? I hope so. Now, fluoride is of course going to have an initial concentration of 0. Now as this reaches equilibrium, the HF concentration is going to decrease by some amount that I will call X. So it's going to decrease minus X. These ions are going to increase by the same molar amount because once again they're present in a 1-to-1-to-1 ratio. So I'm going to write plus X here and plus X there. So the final equilibrium concentration is going to be just adding rho 1 and rho 2. For HF it's going to be 0.15 minus X. For H plus it's going to be 0.05 plus X. And for F minus it's going to be 0 plus X, or in other words, just X. Hopefully you're okay with that. Equilibrium Ka is going to be equal to the concentration at equilibrium of H plus multiplied by the concentration equilibrium of F minus divided by the concentration at equilibrium of HF. Or if we put in each of these values for those terms, it's going to be equal to 0.05, if I can write that neatly enough, plus X, that's the H plus equilibrium concentration, multiplied by X, that's the F minus of fluoride equilibrium concentration, all divided by the equilibrium concentration of HF, which is 0.15 minus X. So I have to set this stuff equal to this number and solve for X. I'm going to go ahead and move that stuff down here to give us some more room. There is a trick that we can do, and I realize it's not 100% totally technically perfect, but it is close enough. And that is, right here in this term, the X number is going to be very, very, very small compared to the 0.15. The reason is because HF is a weak acid. It dissociates by an amount, but that amount, X, is very small compared to its initial concentration. So I can just cross out the X here and leave the 0.15 behind. Similarly, the amount by which this initial concentration of H plus increases is also going to be very small, compared to 0.05 at least, so I can cross out that X. So it's a way of simplifying things, and it actually turns out to be close enough that for all intents and purposes you get the right answer. So I'm going to simplify this then to be 0.05X divided by 0.15. That is all equal to this number, 6.8 times 10 to the negative fourth. If you do algebra and solve for x, you end up getting 2.04 times 10 to the negative third. That is x, and that is the fluoride ion concentration, which is the first half of this question. The second half of the question is asking for the pH of the solution. pH, of course, is going to be equal to the negative log of the hydrogen, or H plus concentration. So what I can do then is set that equal to negative log of 0.05 plus x. We now know what x is. X is equal to 2.04 times 10 to the negative 3. Now you might notice when you throw in 0.05 plus 2.04 times 10 to the negative third that it's so close to 0.05 that it might actually be 0.05. But you chuck that into your calculator, that should give you the final pH for this solution at equilibrium.